So now let's look at this question where we have a container right here, and the container has a volume of 3 liters, and the temperature is 290 Kelvin, and the exterior pressure is 1 atm. And so a reaction is going to happen, and the volume is going to go from 3 to 4, and the temperature is going to go from 290 to 300. And so both the volume and the temperature increase. And what the question wants to know is, what's the sign of the work, and what's the sign of the enthalpy? And so first let's talk about the sign of work. And to talk about the sign of work, what I'm going to do is I'm going to make a diagram of a container like this, and I'm going to put the lid of the container about halfway, about right there. And what we're going to do is we're going to talk about how the work can change values based on if this lid right here goes up or down. And you may have taken a physics class where you've talked about work, but in general, what you need to know is that work is going to be equal to a force times a displacement. And what you need to know is that if you have a box or some type of object and you're going to push on it with a force, so I'm going to push on it to the right like this, I'm going to make the force right here, and it's going to be positive because I'm going to make everything to the right positive. And if I have this box right here and I push on it to the right, it's going to move to the right like this. And so it's going to have a displacement to the right. So I'm going to make this displacement a positive number. Now, if I have the work here, and that's going to be equal to the force, which would make a positive number. So I'm going to have positive times another positive number here. I'm going to have a positive times a positive. So I'm going to get a positive number for the work. And this is what you need to think about in terms of work, in terms of this top of this container being moved. Just like this box was moved, this right here container, the top of it, can also move. And when you have something moving, then you're going to have some work done. And you may also see this in terms of like different types of metals in chemistry, where the metal might expand or shrink. And if it's going to expand or shrink, there's going to be some work done. So we're going to talk about how expanding and shrinking can influence the sign of work. But you need to know that work operates kind of like this. But we're not going to use force. What we're going to do instead is we're going to talk about pressure. And you need to know that pressure is going to be equal to an amount of force divided by an area. And so what we're going to do, instead of talking about work in this definition with force times displacement, what we're going to do is we're going to talk about work as being equal to the negative pressure of the external pressure times a change in the volume. And what you need to know is that there is going to be gas molecules inside of this container and on the outside of the container. And so I'm going to go put those gas molecules in here. They're going to look kind of like this. We're going to put a gas molecule in here, and it's going to go around like this. This gas molecule can move around kind of like this. And then I have some on the outside like this, going around here, and may have a gas molecule going kind of like this too. And what's going to happen is the exterior pressure right here is going to be a 1. So I'm going to put the pressure exterior is going to be equal to a 1. And maybe the pressure on the inside, if this container is being pushed up, I'm going to make the pressure of the interior, PIN, like this. Any number greater than a 1 would work, but we'll just go ahead and we'll make it a 5. So if I have the interior pressure is 5, and it's going to be ATMs, and the exterior pressure is 1 ATM, that means this lid right here of this container will be pushed upwards like this. And so what we have here in this scenario is we're going to put the container down, and I'm going to put the lid of the container closer to the top, like this. And now that the lid is close to the top, that means that the volume inside of here increased. So the change in the volume for this went up or increased. And so what we have here is some work that was done, and we can calculate that work. And so that's going to be the work. It's going to be equal to negative pressure of the exterior. So that's going to be a 1. So we're going to put negative 1 down. And then we'll do the change in the volume. That's going to be final minus initial. And the final volume is 4. So I'm going to do a 4 minus a 3 right here. And so when I do this, I'm going to get that the work is equal to negative 1, and that's going to be in atmospheric liters. And an atmospheric liter, that's a form of energy. You can convert this to joules or kilojoules, maybe in a different problem, but we just need to know that this is going to be negative. And if we go back and think about this part of the problem in here, how we have the force is being pushed to the right, the displacement goes to the right, so therefore the work right here is going to be positive because we make everything to the right positive. Well, in this scenario in here, I have the exterior pressure is pushing down. We have a pressure here that's going to be pushed down, kind of like this. The pressure is going to be going down like that. And look, the volume is getting larger. So the volume's going one way and the pressure is going a different way. And so imagine if we had a force going one way, but it displaces a different way. That wouldn't be positive, that would be a negative. So for this scenario, what we have is the work right here is going to have to be a negative value. So anytime the volume like this would expand, work will always be negative. And so now let's do the opposite of what this is. Let's go in on the other direction. Let's say the pressure of the interior part of this is, we'll make that like a 0.5. And so we say the interior pressure is 0.5 atms, and we'll go ahead and leave the same exterior pressure up with the pressure exterior. We'll go ahead and still make that 1 like this. And so now we have a larger exterior pressure than the interior pressure. So this top part of this lid would actually get pushed down because pressure goes from high to low. And so here is the new container like this, and I'm going to put the lid of the container closer to the bottom like this. And so what we have here is the change in the volume is going to be decrease or go down like this. And so the work for this would be, the work with this would be positive because we have this direction of it going down, and then we have the volume also going down. So they're going in the same direction, and it makes sense that they're both positive, so we would get this be positive there. And this negative right here, this just takes into account basically the direction of the external pressure. Now, you don't want to take into account the internal pressure because the internal pressure is changing, and the reason why this internal pressure changes is because of this equation right here. We have P1 V1 equals P2 V2, and so as the volume gets larger, the pressure goes down. If we were to take this container here and we were to push it down like this to become smaller, then the pressure would also go up. And so if it starts off at 0.5 for this scenario, it's going to be 0.5 we start off with, and it's going to get smaller, and this pressure here would go up. This pressure inside of here, once you get to this point, if it no longer moves, this container no longer moves, this interior pressure and the exterior pressure would be the same number. They would both be 1. And so at equilibrium at this point, the pressure of the interior would be equal to the pressure of the exterior at this point. And so now that we got the work figured out, we need to talk about this change in enthalpy. But before we talk about the change in enthalpy, let's talk a little bit about the system versus the surroundings. And the system can be what we define as what we're interested in. So we're interested in what's going on inside of this container. So this would be the system and this would be the surroundings. And what you need to know is that the system, for this case, the system does work on the surroundings. So the system does work on the surroundings in this case because the system is pushing the surroundings out the way. But in this case over here, we have the surroundings right here. Everything over here is the surroundings, right? That's the surroundings, and this is the system. The surroundings does work on the system. And so a little bit different here, but how this relates to the change in enthalpy is we need to know what the system is and what the surroundings is, because this temperature right here, that's going to be the temperature of the surroundings. It's going to be what we measure of this container right here. There's a reaction that takes place inside the container, and that reaction is going to be part of the system. And so for the heat part, what we can do is something like this. We can go ahead and say that we have the system here. Here's my system, and then we have the surroundings. Now the surroundings is going to be everything else. So I'm going to do the surroundings kind of like this. And what I'm going to do is I'm going to say the surroundings is what we're measuring, and that gets hot. So this gets hot, or at least it increases in temperature. And the only way for the surroundings to get hot is it must have absorbed some amount of heat. And where it got that heat must have been from the system. So the system must have given heat to the surroundings. And if the system gives heat to the surroundings, it means that the delta H value for the system, or which is also the reaction, this is also the reaction, that must be a negative value. So for this answer, we need to get a negative value for the delta H, and we want a negative value here for this work. And so our answer choice is going to be A.